Chapter 7, Section 9 is entitled Scatter Plots. And in this section, our objective is to display and analyze data displayed in scatter plots. We'll begin with the essential vocabulary for Chapter 7, Section 9. Begin with scatter plot. A scatter plot is a graph with points plotted to show a possible relationship between two sets of data. A graph with points plotted to show a possible relationship between two sets of data. Correlation is a description of the relationship between data sets. A description of the relationship between data sets. A positive correlation is defined as two data sets having a positive correlation or relationship when their data values increase or decrease together. Two data sets have a positive correlation or relationship when their data values increase or decrease together. Negative correlation. Two data sets have a negative correlation or relationship if one set of values increases while the other decreases. Two data sets have a negative correlation or relationship if one set of values increases while the other decreases. And no correlation. Two data sets have no correlation when there is no relationship between their data values. Two data sets have no correlation when there is no relationship between their data values. What I want you to think of when you're thinking about a scatter plot is making a line graph, because it's kind of the same thing. The only difference is, other than it's not about time, is that in the scatter plot, you're going to do the dot part, plotting the different things, but you're simply not going to connect those dots. And other than that, it really looks a lot like a line graph. The only other exception would be, as in a single line graph, you would never have more than one thing that corresponds to an x value. For instance, you would never have two dots stacked on top of each other. Think about a north-south alignment or an up-down alignment. It is possible in a scatter plot you can have dots that are in the same north-south alignment, or same thing, have the same x value but different y values, if you want to talk about it in terms of the coordinate grid or the x and the y axis of making a graph. So here, we're asked to use the data to make a scatter plot, and we're supposed to describe the relationship between the data sets. So as you can see, what we have here are actually three lines of information. We have the type of endangered species that we're representing in our graph, mammal, birds, etc. And then here we have what we assume to be the number of those animals remaining in the United States and the number of those animals remaining in the rest of the world. Now, if we were thinking about making, for instance, a double line graph, we would say that this is what's going to go across that x-axis when we make the graph in a minute, and that these numbers are going to be what we're going to match on the y-axis, and then this would be a double, one set of numbers connected for US and another for the rest of the world. But that's not what a scatter plot's actually looking at. A scatter plot usually represents two sets of numbers. So you're actually not going to put this information on the graph. It's going to be this number and this number combined to make a dot, and this will not actually show up on the graph at all. So, as it says in step 1, we're going to determine the scale and interval for each axis, placing the number of animals endangered on the US on the horizontal axis. So these US numbers are what's going to go left to right when I make my graph in a moment, and the number in the rest of the world on the vertical axis. So these are going to go on that y-axis that goes up and down when I make my graph. And you can see here as I toggle to the next slide that indeed your graph does not have that mammal listing or any of those, the U.S. numbers are set up on the x-axis and the rest of the world numbers on the y-axis. We'll plot a point for each pair of values then. So let's start off and look at the numbering here. Remember, as we are accustomed to on this y-axis, we go up by the same amount from jump to jump to jump. And notice the numbers that are actually show this going up by 60. 60 to 120 to 180 to 240. Notice the graph really doesn't go up by 60 though, because they've left a blank between each one. So really the graph in terms of the actual grid boxes is going up by 30. For the US numbers, you have to do the same thing. You have to go up by an even amount. It looks like it's going up by 20s, but if you look here, there's one empty box between each marker, so it's really going up by 10s. They just didn't label each one of the axes here. Okay, so once you lay down your numbers, then you're going to go ahead and make the dots that correspond to each pair. So for instance, the mammal number in the US was 69, and in the rest of the world was 256. So you're going to figure out where mammals 69 would be, which would be here, just to the left of the 70 marker. You're going to go up until you get to 256, which is above the 240 marker, and then put your dot there. And again, that 256 corresponds to what you would have over here, where 256 would fall. Notice that they really didn't make the most proper of graphs, because they knew our graph went up to 256, but the top marker they're actually showing us is 240. That's not really proper. They really should have gotten up to 256, which going by 30s they couldn't have done, or gone over it. So they really should have at least, at the very least, included one more grid line going across to show that they got to 270. But as you can see, that is why the graph is drawn with these lines protruding up. But not really the most proper graph, but not necessarily wrong either. And you'll continue down that list. So for birds at 75, for the US number, which we assume is this one here, because that would be about halfway between 70 and 80. And as you can see, that dot hits for the rest of the world number at 176. So if I read across, that should be about where 176 falls on the y-axis. The reptile number for the US is at 13, which looks to be one of these two. These do look to be very close. However, we see that the rest of the world number is 66, which means that one has to represent 66. As we slide to the left, you can see that would match up with 66. The amphibian number is at 13 for the US and 8 for the rest of the world, so that's going to be this lower dot here. Again, these two do look very close, but very clearly that's the one that's going to match up to 8, not this one here, 8 for the rest of the world. And then finally, the fish number at 74 and 11, so that's going to be this lower dot here. Again, these two do look, again, very close, but clearly the one that matches up for 11 on the rest of the world is this one here as we read to the left. And notice here then we're going to label the axes, US and rest of the world, and we gave the graph a title in number of endangered species. Now they're then asking about the relationship between the different data sets. There were 3 different relationships that were described in the definitions: a positive correlation, a negative correlation, and no correlation. And remember, they used the word correlation to mean relationship, which is, again, a piece of information they've actually already provided to you. If we want to talk about what a positive correlation would look like, consider the dots that are on your graph. If I were to draw a line through the middle of the dots, or so there would be an even number of dots generally above and below a line should I draw one on the graph. In this scenario here, notice that when I draw the line, it tends to trend up, in that when the numbers get bigger on this axis, they also get bigger on this axis. That's what's called a positive correlation, or a positive relationship. One number gets bigger and so does the other. It doesn't have to be true for necessarily every single point, but it should be true for most of them. A negative correlation is quite the opposite. A negative correlation, if I had my dots, if I were to draw a line through them, that line would tend to trend down. What's happening there? One of the numbers, the x-axis numbers, are getting bigger, while the other one is getting smaller. That's what a negative correlation is. No correlation will appear a couple different ways. No correlation could be that there are just dots kind of all over with no necessary pattern between those dots, no relationship between those dots. If I drew a line really to match these dots, it would probably be pretty much a left to right line, a horizontal line, and that indicates there's no relationship between the data. Yes, one value might be getting bigger, but sometimes the other number is bigger and sometimes it's smaller. And indeed, it could be just that the lines, the dots rather, are much closer together, but if I were to draw a line that separated them, it would go left to right. And indeed, that shows no correlation. So again, no correlation could be that the dots form a left to right line, or that they would be all over the place, but still basically a left to right line. And as you can see in this graph, other than maybe absent of a dot up here, you have some dots in the lower left, some in the lower right, and some in the upper right. Clearly, there's no relationship going on here. Sometimes the one number is bigger and the other number is smaller, and vice versa. There's no inherent relationship between those different dots. So now they're asking us to write positive, negative, or no correlation in example 2 to describe the relationship. And as you can see, the graph there is comparing the area of a country with the population of a country. Now, without even a graph, we should kind of know what's happening here, because logically, the more space I have, the more people that should be able to live in that space. So the more space I have, bigger number, the more people that can live there, bigger number. Well, as we just described, that's a positive correlation. And indeed here, the graph shows that area is increasing and the population increases as well. So that's showing a positive correlation. Again, if I was going to draw a line that kind of splits these dots into two parts, I would probably draw my line like this. Notice it does not necessarily start at the left side, but it does go up as we go from left to right. It does happen to go through a dot, but we have about the same number on one side as the other here. Since that line goes up, that's a positive correlation. Height and the number of vacation days. Now notice there is no graph shown here, but they're asking you to describe the relationship. So they're asking, is there any correlation between how tall a person is and the number of vacation days that person gets? And obviously that would not make any sense at all. The height of a person is not related to, in any way, shape, or form, how many vacation days you get. Look around at your classmates right now. Think about it. The person next to you is probably not the same height as you, but they get the same number of days off school as you do. All right? There's no relationship between those two pieces of information. Perhaps if we said height and weight, there might be a little bit better of a correlation, not necessarily always, but generally, the taller you are, the better chance you have of being a little bit heavier in terms of weight. So we could have a correlation there, but height and number of vacation days are two totally unrelated details. Okay, so let's go ahead and take a look at the concluding examples here. Here they're asking us to use the data to make a scatter plot, and then they're asking us to describe the relationship between the data sets. And as you can see, the graph is comparing the year and the number of people that worked on farms in that year in thousands. Now, of course, as you already know, this graph would probably be a little bit better represented with a line graph, because it does look at data over time, and that's what a line graph is supposed to do. But we do have a data set that corresponds here, a year being matched up with the number of people, and that's really what you need to make a scatter plot. So a scatter plot is indeed acceptable here. So, as you can see, I've set up my graph with the title, the number of farm workers. Down here I'm putting those years, and notice they are even increments. Notice, again, they do look to be jumping by 20 years, but there is a gap in between each one block, so it's really a 10-year span. Going up the y-axis, again, those numbers do appear to be going up by 2,000, but again, there's an empty block in between each gap, so it's really going up by 1,000. Label year, label number in thousands in parentheses. And so you have all the properties of a well-prepared graph laid down there. You do not need a legend or a key ever in a scatter plot because you could only ever be comparing two sets of data. In this case, by two sets of data, I would imply year being one set of data and the number of farm workers being the second set of data. So the 1940 number is at 8995, so we'll go up from 1940 until we reach 8995. If we go right to the 9,000 marker and then just drop a little bit below it, you're at 8995. The 1950 number is at 6858, so we go up from 1950. If we go to 7,000 and then just drop down a little bit beneath it, that will work for 6858. The 1960 number is at 4132, so I'm going to go up from 1960 till I reach 4,000 and then go up just a smidge for 4132. 1970, again, between the 1960 and 80 markers, they did leave us a block there. That would be 1970. That number is at 2881. So I'm going to go up to 3,000 and just come down a little bit for 2881. Now notice the 80 and 90 numbers, even though they are a little bit different, all right, really in terms of the graph, because they've used such a large scale, don't appear to really be any different. The 80 number, 2818, goes down just a slight bit from the previous dot, and the 90 number actually comes back up, but just a little bit, and just a little bit from that 80 number, but it's still beneath that 1970 number, so you see a very shallow V forming here at the end. And that's your scatter plot. Remember, you do not connect the dots here. That would then make this a line graph, and that's not what we're doing, even though this compares time. Now, if I were to draw a line that kind of represents these dots, it would probably be something like this. Notice in the beginning, that line would actually be very good. At the end, though, it's really not as good because the graph is so flat at the end. If I was connecting the dots, if I was making a line graph, this would kind of like be an L, but this part that would usually go straight up is kind of tipped out a bit. It really is not the best. However, very clearly, as we go through time, years are happening and these numbers are coming down. So this is a negative correlation or a negative relationship in that the number of farm workers is very clearly decreasing over time. Perhaps not always, but overall, if we look at 1940 to 1990, very clearly the numbers have gone way, way down. Okay, and finally they're asking us to write positive, negative, or no correlation to describe the relationship here. And very clearly, looking at these dots, if we were to connect them, which we won't because that would make it a line graph, but if we were to connect them even, or try and make a line that has the same number of dots above and beneath it, that line would be falling from left to right. Look at the information. As the length of the string, and as you can see, the graph is about guitar string frequency. So when I'm talking about the length of the string, I'm talking about the length of the guitar string. As the length of the string is decreasing, or rather increasing, the number of vibrations it creates per second decreases. Right? As you can see, as we go up this way, these numbers are actually coming down. All right? And that is a negative correlation. One's getting bigger while the other is getting small.